Good morning to everybody and welcome to this CMCC Lectures. And I'm Manuela Balsarolo from CMCC and I will moderate the lecture, and with me there will be Sohail Shaib as a discussant. And this lecture of today, it's it's done by Sandy Harrison. Sandy Harrison is a professor of global paleoclimax and biogeochemical cycles at the University of Reading. She is also a CMCC Bassi Fellowship, and during this lecture, she will showcase new approaches to model wildfires, and including new development that can be done using empirical data-driven models, machine learning, to simulate wildfire behaviors, and also to capture extremes behavior and uncertainty in wildfire. And she will talk about the application on evolutionary optimality theory, and on the interaction between vegetation and wildfires. This lecture is hosted by a CMCC lecture web series. And before leaving the floor to Sandy, I will introduce briefly CMCC and what we are doing. CMCC is the European Center on Climate Change, and we are leading research in Mediterranean area, and we focus on the understanding of interaction between climate and society. And CMCC has a very broad network, and as a lecturer, and he participates in many projects linked to climate change and society, and the impact on vegetation of climate change on vegetation. And we have a network of about 70 countries, and we have collaboration among European countries, but not wholly. And we have projects in collaboration with partners in outside Europe as well, in Africa, US, Japan, China, and India as well. And this, thanks to this broad network, we aim to build up solution starting from a robust scientific background and from a different kind of model. And what we produce is advanced climate research using multidisciplinarity approach and analysis, and combining different climate modeling. And we also work on impact assessment and environmental economics. And our mission is also to support science-driven adaptation and mitigation action to convert what we are doing in actionable tools that are useful for policy makers. CMCC has an infrastructure that is organized in a different level, and to foster the transversal and multidisciplinarity collaboration, and it combines different classes of experts on modeling and modeling climate change impact and environmental economics. So in this structure, we have 3 multidisciplinary research institutes, 4 strategic program, a computing infrastructure center, and 2 center on one on digital innovation and another one on high-level education and training. About the research institute, the 3 research institutes are one on Earth system prediction, another one on climate resilience, and we have an European Institute on Economics and Environment. All these institutions work together with a common aim and to make synergy between to fulfill a big question in science, climate science, and to support decision making. In about the strategic program, this strategic program focuses on four very relevant and questions. One is about the carbon cycle, one is on global cost, and one on the interaction between socio-economic outcome in a changing climate. And the last program is on integration of artificial intelligence and machine learning. In this program are supporting the activity of the institute and the collaboration and synergy with other partners and institutions in the projects. So about the centers, the High Performance Center, it's where all climate analysis and prediction are run, and it's really related to climate change research. And the Advanced Digital Innovation Center address critical research needs, and it's linked to innovation and digital innovation. It serves the research of the center, of the research center at CMCC. And in the Advanced Training and Education Center, we focus on the education, on exchange of knowledge and people on the climate change. And this is thanks to this training center, we build up many initiatives like training school, summer school, to form a new expert on climate science. In these lectures, it's very active at CMCC, and thanks to this series of lectures, we had the opportunity to invite a CMCC expert from different international institutions, and we had already 4 different lectures, for instance, from experts from University of Colorado, Jeffrey Weiss. He talked about climate forecast. Antonietta Capotondi from University of Colorado and NOAA. She introduced new research on ocean extremes, and Samantha Sieldeki, she talked about acidification in the ocean, and we had also a lecture on water resilience done by Patrick Michael Reed from University of Cornell. All these lectures are accessible and can be are recorded and provided on CMCC website, and link through this QR it's possible to listen the lecture. And we will have soon a new lecture from François Cohen, and this is on the effect on temperature on health and how people can adapt to extreme temperature. And it will be in June, and by scanning this QR code, you can register in. So some rules about this this lecture. So, and how we manage it. Your audio and video are deactivated by default. At the end of the lecture of Sandy, there will be a Q&A session, and you can ask a question by writing on the chat directly, and we will follow the chat, and we will pose to Sandy questions. So Now I leave the floor to Sandy, and Sandy will give us most recent advance on research on wildfire. Thank you, Sandy. The floor is yours.
Thank you, Manuela. I am delighted to be able to give this lecture. You need to stop sharing, Manuel.
Yes. Can you share now?
I should be sharing now.
Yes. Can you put in a presentation mode?
Yes.
Okay, perfect.
I'm delighted to be able to give this talk, and I'm very pleased to see so many people online. What I'm going to talk about is modeling wildfires. I hope. So wildfire is a fundamental part of our world. If we read the newspapers, we tend to think about wildfire as being something that is very bad for the environment, and obviously a lot of fires are, but wildfires are also something that is necessary to preserve biodiversity, for example, in the savannas, to initiate succession. It's part of the way that the biosphere has evolved through time. So wildfires are not going to go away. And about 4% of the planet burns every year. So it's a non-negligible issue for us. And wildfires are also important because they have impacts on all aspects of the Earth system. So they, as I've said, they influence the biosphere through changing community assembly, through moving biomes, through influencing biodiversity, and through selection of traits for reproduction, for example. But they also have an impact directly on the climate and the carbon cycle through emissions and through changing clouds and albedo. And they have an impact on the hydrosphere via nutrients and changing productivity and so on. So they are intimately connected with everything that drives the Earth system. We've seen reports like this Spreading Like Wildfire report recently, which suggests that burnt area will increase over the 21st century quite considerably in response to climate change. And we've also seen in this report that the likelihood of catastrophic wildfires is going to increase. These are based on, sorry, let's go back. Okay. These reports are based on using machine learning with models of wildfire. So this particular report was based on the EasyMIP2 models. So in a sense, these predictions are very contingent on how well our fire models actually do. So when we started FireMIP, the Fire Modeling into Comparison project about 10 years ago, we were very pleased to see that we were actually in the ballpark in terms of our simulated burnt area. So we were saying if you ignore the oldest models, which in this case were GlobFirm and MC2, which really don't perform very well, we were saying that we were getting burnt area globally in the same ballpark as the observed burnt area, given the uncertainties in the observations. However, when we look at that in detail, we did an analysis here where we compared those predictions for the individual models against the four observed data sets that we had at that time. And we looked at both the burnt area spatial pattern, the seasonal phase, the seasonal concentration, and the interannual variability. And we compared our models with two models, one that was a random model, so effectively sampling the observed burnt area randomly, and then one where we took the mean burnt area and applied that over the whole of the globe. What you can see here, the brown colors in this plot show where the models are predicting worse than a random choice. And you can also see that there are a number of places where the models are slightly better than the mean, but not very much better than the mean. Even in the best cases, when we look at burnt area, very few are better than 25% better than using a mean value. So although the ballpark was right, the details were wrong. Okay, so that was models of a generation of 10 years ago. So what's happening now with the models that we're using? So here's an analysis that we did looking at the CMIP6 simulations in the last round for the IPCC. And we're comparing that with the previous set of simulations from CMIP5. So this plot shows burnt area on the top and fire-related carbon emissions on the bottom from the observations from CMIP6 and from CMIP5. Well, the good news is that CMIP6 models appear to be doing better than CMIP5. On the other hand, for burnt area, they still underestimate the observed burnt area. And then for the emissions, for which most of these models were tuned up, they're better than CMIP5, but they're still largely overestimating carbon-related emissions. And if you imagine this then feeding back into the climate, these are all coupled climate models, Earth system models. If you imagine this feeding back into those models, it's meaning that the fire, the good simulations of the fire are going to affect the carbon cycle, are going to affect the climate, and are going to affect how much warming we actually see in those simulations. And we can look at that in some detail for individual models. So here I'm showing on the left burnt area and on the right the carbon emissions. And the dotted lines through here are the average burnt area as seen from observations with the uncertainty shown in a grey bar. And what you see again is that virtually all of the models are on the very low end and some way outside the ballpark. And some of these, EC Earth, for example, are state-of-the-art models, but nevertheless are really underestimating how much burnt area we have at present day. And even in terms of the emissions shown on the right here, there's a lot of underestimation of the observed emissions. So we are still not doing very well. And if we then go even further into that and look at the seasonal cycle, so the plot on the left here is the seasonal cycle of burnt area, and the plot on the right is the trend in burnt area since 2000. What you see in black is the observed, and you can see from this that in terms of the seasonality, the models can be up to 3 or 4 months out in terms of when the timing of fire is compared to observations. And similarly, none of the models are able to reproduce the long-term trend since 2000. So why do these models perform so badly? Well, I think there are 4 reasons for that. I think, first of all, there's the drivers that they're using. The hypotheses that have been incorporated into models about the controls on wildfire are very often not correct. The second thing is that these models are largely deterministic, but both climate and wildfire are stochastic, and we have yet to find a good way of dealing with this stochasticity when we make predictions. The third thing that I think is wrong with these models is they're increasingly complex. As we discover new things about the world, we say, let's put that in our model. And so we put new processes into the model, and we incorporate those without consideration of how those processes interact with other processes already there, and very often without independent testing of the individual processes. And then the final thing I think that is wrong with the model is that these models are tuned for modern conditions, but applied to the future without being tested in so-called out-of-sample states. And these are issues that I'm going to try and cover briefly in this lecture. So first of all, to look at the hypotheses about the various controls. Again, this is some work that was done a little while ago, but the models haven't improved, which is comparing the emergent relationships between burnt area and various controls like maximum temperature or the number of wet days or diurnal temperature range or population density, for example. And the black lines and the gray bars are the emergent relationships if you analyze the data, and the colored lines represent various fire-enabled vegetation models. And one of the things that you see, well, two things that you can see here is one, the models are all doing very different things. But the other thing I think you can see is that in most cases, the relationships that they have with these supposed drivers do not look like the relationships that we see in the observations. So in other words, the controls that have been incorporated into the models are not the correct controls. And the second point I wanted to make here is about the complexity of the models. So this is a chart that Sam Rabin did many years ago, trying to show the processes that are incorporated in our current state-of-the-art models. And he's taken individual models here, which are the colored bands, and the processes are listed going up. We start off from what causes fire ignitions, and we go through several processes that determine whether there is an ignition and whether that ignition starts a fire, and therefore whether there's an actual fire count. The second panel starts from that fire count and then goes through all of the processes that might influence the area burned. So individual processes like the speed of spread, the amount of fuel, the drying of the fuel, the wind speed, and so on. And then finally, once you've got area burnt, there are a number of other processes that are incorporated to determine how much damage that fire is doing in terms of either combusted biomass or killing of biomass. Again, what you can see is all of the models have very different approaches to doing these different steps, but the number of steps that they have to go through is very large and very complex. What they test is the area burned, or occasionally the combusted biomass, which is your carbon emissions effectively. But all of these individual processes that make up the models are not tested independently. So then I want to talk a little bit about the whole issue of stochasticity. I think we're all very familiar with the idea of looking at the weather forecast before we make a decision about whether to go out. Here is from the Met Office the hourly probability of rain tomorrow in Reading. And from this, you can see that if I'm going to go out in the morning without an umbrella, I had better do it before 11 o'clock in the morning because the probability of rain increases through the day. These predictions of the probability are based on an ensemble of simulations which differ from one another in trivial ways, but all are consistent with the climate of the current moment. Now, we can use this probabilistic approach using an ensemble to look at fires. So weather and fires are both stochastic. You may have the absolute right conditions for a fire, but whether one starts is by chance. Here, what we've done is to take an ensemble of modern climate simulations. So we've got 1,600 model years that represent the interval between 2000 and 2009. That's shown in blue here. And then we've got another ensemble of a similar size, which is represents a 2-degree warming compared to the modern. And we're looking here at the annual number of fires in the United States. What you can see here is that there is a probabilistic distribution in terms of the number of fires, and that gives you quite a range. So you could have, under modern day conditions, as few as 20,000 fires across the US, or you can have more than 60,000 fires. And then as you go into the future, that range shifts. But again, there's a very large range so that you can have similar number of fires as you could get today, or you could go into very much higher, almost double the number of fires. If we look at this in terms of spatial patterns, we can see that under the modern condition from this ensemble, when we take the mean of the ensemble, it looks very much like the observed record of the number of fires, which I'm showing on the left here. But if you look at the spread, then the spread is very large, much larger than you would expect from the mean. And that spread, the relationship between the mean and the spread, is not consistent regionally. So there are some regions, so for this belt along the central part of the US, we've got a lot more spread than we have compared to the mean. And again, if you go into the future, you can see there is a shift in the mean values in the future, but the shift in the range is very much larger than the shift in the mean. This also affects the length of the fire season. So here, again, we've been comparing the mean and the maximum length of the fire season under modern conditions with this ensemble of climate and also under the 2 degrees C. What you can see is that there could have been, under modern climate conditions, a much longer fire season, particularly in the Western US, than we actually saw. And as you move into the future, that length of the fire season increases till it almost represents the full year as being suitable for fires or fires occurring. If we look at this in terms of the probability distributions broken down by different regions, so the coloured probability distributions here represent the different regions under a modern climate, and the grey is what would happen with a 2-degree warming. One thing you can see here is that, and the bars across, I should say, represent the observed number of fires in decades in the recent past. What you can see here is that in some regions, and I'm particularly picking on Mediterranean California, which is the second one in here, in some regions, the observed fires, the actual realized fires, were very much less than we could have had under our current climate by chance. So we were actually rather lucky in California in terms of the number of fires that actually occurred. Whereas in other regions, and I'm here looking at the Great Plains, which is the third from the end, you can see that we actually had realized climates that were within the full range of what could have happened. So this is interesting because it says that we might have had, in some regions, we might have had considerably worse fire occurrence than we actually saw, whereas in others not. But again, you can see here that as we move into the future, the range overlaps in most cases with the present day possible range, but then extends further. So we are expecting to see a change in the range probability. And just to emphasize this thing about the future, I'm just showing these graphs again to make the case that we may get in the future, if we're very lucky, we may get fire seasons that look very much like things that we had at the extreme in the present day. But actually, the shift, it goes beyond the upper range, and the range goes beyond what we've seen under present day conditions in most regions. And we're also seeing that if we look at the maximum fire season, we could see a doubling of the length of the fire season in these regions. So I think the bottom line here is that we really should be taking the idea of looking at ensembles of climate change very seriously when we're looking at what might happen to fire in the future, and indeed when we're trying to interpret how seriously our fires are operating under present day conditions. So now I want to return to this issue of model complexity, and I want to introduce a so-called eco-evolutionary optimality theory. So one of the problems with models is they have got more and more complex, more and more processes, more and more untested processes, more and more parameters that have to be specified in that modeling context, which we don't know. So we're moving the models into a world of increasing uncertainty. This is true not only for fire models, it's also true for the vegetation component of land surface models and the fire models. So one of the approaches that the vegetation community are adopting at the moment is this approach called eco-evolutionary optimality, which is the idea that on evolutionary timescales and also on ecological timescales, vegetation is adapted to the environment which it finds itself in. And if it isn't, it moves. So here we have a very simple way of saying we don't need to have all of the individual processes. We can use the knowledge of the vegetation to come up with some very simple models which represent the trade-offs that the plants have to do in order to function. So here's a very simple model that predicts with a very few equations and no unknowns the seasonality of FAPAR, so foliage absorbed photosynthetically active radiation, which is related to leaf area index. And so this model, we've got the observed seasonality on the top corner. We've got our eco-evolutionary optimality model at the bottom there, and you can see the seasonality is very well reproduced. And then in the right-hand side, we have the trendy models, which are the ones that are being used to predict impacts under future climate change. And you can see that their prediction of modern seasonality of vegetation is very poor. And just to emphasize that, we've plotted here the models that go into trendy with our PL model at the bottom here, and we're showing that there's an increase in the R squared, and our model is better than all of the others, and a decrease in the uncertainty or error. So this eco-evolutionary optimality approach has been adopted by vegetation and modelers, and my question here is, can we actually use this with simulating fire? So one of the things that empirical studies have consistently shown is that factors that influence fires are fuel load and fuel drying. And you can see this here. If you look at burnt area, you look at fire intensity, things like the annual GPP and the seasonality of GPP and the amount of live grass, all of which determine fuel loads, are really important drivers. And then you can also see that if you look at drying factors, here represented by the diurnal temperature range or vapor pressure deficit, VPD, or the seasonality of dry days, again, these are important determinants. So this opens up the possibility of having an EEO approach to fire. So what we've done here is to take fuel dryness as represented by VPD and biomass production, fuel load, as represented by GPP, and to say that the fire occurrence is going to occur as a result of differences in the seasonal phasing between these two. And then we can look at that in terms of, can we then do a clustering to look at areas where we might have different fire regimes as a result of this. So I'm looking at those clusters again now. These are clusters that have been simply derived by looking at the magnitude and the phasing differences between VPD and GPP. And you see that this is able to identify specific clusters which look very much like the vegetation underlying those regions. And if we then look at what fire properties there are, and here I've listed the clusters by number 1 to 18, and then the fire properties, so burnt area, fire size, ignitions, carbon emissions, and so on. One of the things that you see from this is that each cluster has a distinct set of fire properties. So based on this very simple trade-off between fuel loads and fuel moisture, we can get some kind of prediction of what the burnt area should look like. And so we can use this to develop an EEO fire model where we've got fuel load, which we're determining as the fraction of annual GPP that's allocated to leaves, and then with the decomposition rate. And then we have the synchronicity between the production of that fuel load and the drying of that fuel load, and that will give us a propensity to burn. And then if I show you how that EEO prediction looks in terms of the observed burnt area, you can see we've got an observed burnt area and then an EEO prediction of the propensity to burn, but scaled to the same kind of fractional areas. And you can see that the EEO model with these very two simple drivers is able to reproduce the spatial patterns reasonably well with the global correlation of 0.57. And it's also one of the things to bear in mind here is that it has only two variables in here, which at the moment we're prescribing as constants. Okay, we can go a step further using EEO. We can say, okay, instead of having a constant sort of relationship of GPP to litterfall, we can use eco-evolutionary optimality to predict what that litterfall ought to be in terms of it's a function of the leaf biomass over the leaf lifespan, which we can then predict from the maximum possible leaf area and the leaf mass per unit area and leaf lifespan. And this is the global pattern that you see for that. And then if you look down at the bottom corner there, you can see observed litter fall compared to what we're predicting and see that we're actually doing a reasonably good job, again, with a very simple model with very few unknown parameters that we have to specify. So now we can plug into our model actual predicted litter fall. We also need to think about the decomposition of that. And at the moment, we're working with an empirical decomposition prediction model, which takes account of environmental factors, so growing degree days as a measure of warmth, dry days as a measure of drying, and then also takes account of the nature of the leaves that are being produced in terms of the C to N ratio, which is a function which determines how quickly they can break down. And again, you see that we've got a nice spatial pattern of this decomposition rate, which is highest in tropical areas and lower when we get into the tundra areas. And if we compare that with predicted versus observed decomposition rates, again, you can see that first order, we're doing a reasonably good job. So now we can replace those constants with a predicted decomposition. And then from that, we can predict the steady state fuel load, where we have fuel load as a function of litter fall and then K, the decomposition rate. And again, you can see that we can now come up with a reasonable prediction of what the fuel load should look like across the globe. The predicted levels are much more restrained, if you like, than the observed, because litter fall is quite heterogeneous. But nevertheless, to first order, we're getting the right sorts of predictions. Okay, the final thing I want to talk about is the importance of out-of-sample testing. So we tune up our models, whether they're climate models or vegetation models or fire models, to reproduce the modern observed patterns, because that's what we have. But we then apply them into the future, and the future is very much different in terms of forcing from what we're seeing at the present day. And the question then is, how well can our models reproduce that future? The last glacial maximum, the LGM, experienced a change in climate that was as large as we are expecting under moderately high future scenarios. It's the opposite sign. It's a cooling and a drying compared to the future, but nevertheless, it is a very large change. What I'm showing here are the models that did paleoclimate simulations for the last glacial maximum as part of CMIP6. One of the nice things about the last glacial maximum is we can reconstruct the climate using pollen data, and that's the black cross shown on this figure on the left. And the colored dots here are the various models that took part in CMIP6, and the squares are actually the CMIP5 models. What you can see is that there are very few models that reproduce the observed change with its uncertainty of the difference in temperature between the northern extratropics and the northern tropics. We can come a little bit closer to present day and we look at the mid-Holocene, which is the graph on the right. Mid-Holocene was characterized by a change in orbital forcing that caused warming conditions in the northern extratropics and moistening conditions, the expansion of monsoons in the northern subtropics. In this chart, the colored lines are the various models from CMIP5 and CMIP6, and the gray bars are the observations of that temperature change in different regions across the world. And again, you can see that the models are underestimating the degree of temperature change in many of these regions. The key point about this is that what this says is that climate models that we're using to predict the future are not capable of predicting known features of the past that were as large as what we're expecting to see under climate change. So I want to make a plea that we should do the same with other models. We've done the testing for the climate, but we could also do that testing for other kinds of models. So here's a preliminary test looking at the simulation of the last glacial maximum fire regimes using an empirical model of annual burnt area, where blue means that the fire was reduced compared to present, and pink means it was increased compared to present. And the dots on here correspond to charcoal records, which provide an indication of the kind of change in fire regime that was experienced. And you can see to first order that many of these records also show a reduction, overall reduction in fire. And some of the records show an increase in particular places. So for example, in Alaska, which is predicted from the model, but there are still places where the observed and the model do not agree, and therefore where there's some problems with the models that we're using. But I want to show this to say it is possible for us to test fire models against observations in the past. So I want to finish here with a few take-home messages. I think the key point for me is that the current state of our models means that they are not fit for purpose in terms of predicting the future. That in terms of fire, we do need a better understanding of the controls on fire properties. And we do need to consider the stochastic nature of both climate and wildfire when we're making predictions. I do hope, and I am pursuing the idea that eco-evolutionary optimality approaches may offer a simpler and better way of modeling vegetation and wildfire. And I also want to finish by saying that I think we really must develop a more extreme way of testing our models if we want to have confidence in their ability to predict the future. And with that, I'd just like to thank some past and present members of my team who have contributed to these analyses. And I'm very happy to take questions.
Thank you very much, Sandy, for your impressive presentation. And how we will do now, I saw that there are already some Q&A, some question comments in the chat. But first, I will leave the opportunity to Sohail, our colleague and he's the director of the Carbon Cycle Program at CMCC. And as you know, we are working on, we are very interested on fires. So, and I would also tell the audience that with Sandy, we are also organizing, we are organizing a session, a special session on fires during the week in London for London Climate Action Week that will take place at the end of June. So it's also a very good opportunity to meet in person us and Sandy and share knowledge and questions. So Sohail, the floor is yours.
Yeah, thank you very much. Thank you, Sandy, for very interesting talk. It was great to see how you charted the pathway for improving these models and very great ideas there. So I just wanted to start and asking you, when you were pointing out to the existing model and shortcoming of them, you were mentioning that overall, this model seems to basically underestimate the burned area and overestimate the carbon emission. And the improvement you showed, some of the figures you were showing was mainly about the burned area improvement. But do you also have results for the carbon estimation, carbon emission estimations having been improved through these improvements that you were showing?
Not yet, because we haven't got to the end of the improvements. So I don't necessarily believe that what we're going to do in terms of the feedback to vegetation is going to be correct. But I think that if we can get the burnt area right, then that should, and we get the vegetation cover right, which is the other problem with some of these models, is that they don't necessarily get the right vegetation cover. If we can get those two things right, then I think we should be able to get the emissions right. I think one of the reasons that there's this discrepancy between the model simulations of burnt area and the model simulations of emissions is that because these are actually coming from slightly different process, the processes by which they're generated are different. What happens is people tune up the emissions because they can do that more easily than they can tune up the burnt area. So this is why, in general, and this has been true CMIP6, CMIP5, and previously, and FireMIP, the emissions are always better than the actual burnt area is, which should not be the case, basically, except if you're doing that tuning.
Yeah, that's right. And in terms of resolution, also, I was curious. So, what are the geographical resolution and also temporal resolution of these predictions? How far can we go, zoom in and see, like, we can get a good estimate of the burned area and like how frequent we can get them?
Well, I think for the global fire models, a lot of them are working at best at 0.5 degrees, about 0.5 degrees. So, they're grid cell models. Some of them are actually in the CMIP6 are being run at much coarser resolution of, 2 degrees or something, because that's the resolution the climate model is being. So there is a problem about this. In principle, there's no reason why you couldn't come down to something very small. It's just a question of the computational, well, it's a question of the what the inputs are. So if you're taking climate model inputs and they're at 2 degrees, you have to work at that. But it's also a question of, computational power. So I think that's where the limitation is.
Yeah, just I ask maybe one more question and we go to the Q&A from the audience to give more time also. And please, use the Q&A section as Manuela mentioned and post your questions there. We are gonna start reading them soon. So yeah, maybe my last question will be about when we are looking at the future scenarios, we see more and more wildfire getting closer to the urban area. And so we will have this kind of mixed urban wildland interface. And so the emissions will be very different and probably the burned area dynamics. So I was curious about your thoughts on that, how to model them, how to improve the models.
So I think, one of the real problems here is that it's not clear how much of the wild and urban interface there really is. I mean, if you look at sort of global estimates, it's relatively small. If you look at regional estimates, it can be 50% or 60% of the area. I think that the dynamics of fires when they're actually in urban areas or peri-urban areas is likely to be very different from the way that they're operating in natural conditions. So I think we are going to have to think about how we model urban climates and fires. Now, there are people who are working on that. but it's a different community from the ones that are sort of doing the global modeling. But we will need to move into that.
Thank you very much. So, Manuela, maybe we can start, going through the Q&A.
Time, of course, and there are many comments and questions. So I will start from a comment from Douglas Kelly, and it's about the UNEP report. Let's hope that I will interpret well and summarize it well. So it's this report. It was not actually using EasyMIP 2B fire model. It was using an empirical based model, much more like the Bistiness and Haas model than a fire MIP. EasyMIP just provides bias-corrected meteorological forces. So why? Those critics to a fire MIP model are not applied to a UNEP report. So it's just one comment from Douglas Kelly, and there is also an integration of it, and mainly a question. Have you looked at behind the fire MIP model when categorizing model? There is a huge wealth of non-process-based model. Cone fire and flame are both stochastic empirical based model. POF and base as model base model, and so it's I wonder how this fits into this critique about fire MIP model. So how would those model from a wider fire modeling community could be used to do more ecological and societal impact? So
thank you, Doug. What we have looked at the empirical models, and in fact, we built some of these empirical models, including the Bistinas model and the one that Livia has just produced. One of the problems with that, again, is that the empirical models don't necessarily encapsulate the processes that I think fire is really working with. So, you have the same problem. And again, you can see that when you evaluate those empirical models, they're getting the big picture, but they're not necessarily getting the details of that picture. So I think there's still as much uncertainty. So I wasn't trying to criticize fire MIP or process models per se. I was saying that in a sense, the models that we're using, whether they're empirical models, whether they're stochastic models, whether they're machine learning models, which people have also developed machine learning models, they're still subject to the problem that there are uncertainties about the controls. If we don't have the right controls in there, they're going to not get the right answer. And we're still not testing them radically under past climates, which would then tell us how robust they are in terms of predicting the future.
Thank you, Sandy. And now from Shaba Salvi, it's about the point taking into account climate stochasticity is interesting, but is this data available?
Most climate modeling groups these days are running ensembles. These are ensembles which, start from the same point, but they've got a spin-up period, and they start the simulation from year 1 or year 2 or year 3 or year 4. But essentially, they're trivial differences between the simulations. Now, some modeling groups, so KNMI, which is the one that we used in this analysis for the US, they have a very large ensemble. Other modeling groups only have ensembles of 10 or 20 different simulations, but most modeling groups these days do have ensembles, and you can use them to run your vegetation model or your fire model. And I think the point about this is that knowing that these are all possible modern days, there's not a lot of difference between them, but they can have a big impact downstream on fire is a crucial thing.
Okay, and again, linked to this one, it's about generalized linear model. So another model. How could this be improved, adjusted to represent stochasticity or account for spread rather than stick to the mean probability of burn area fraction? So yeah, this is from Matteo Ruhet.
That's an interesting question, Matteo. I think, one of the things here is, so we're running ensemble GLMs with changes in climate, but then there's also the issue of other factors. So what we've been doing is to use the climate ensemble to drive a vegetation model to get an ensemble of vegetation properties. But of course, it's a second step of modeling. So we can get the climate ensemble, we can get vegetation ensemble, and then you hope that the other factors like topography or people, are going to be constant. But there's also the possibility that we should think about variability in those influences. But I think the key issue here is getting the drivers that you use for your GLM right. Because as I say, we tend to sort of throw things into the GLM and hope for the best. But we need to understand the processes, I think.
Okay, thank you. So let's move to another question. And so one, it's about the prediction in a southern hemisphere across different classes of model. Why these are so different, which is the reason behind, which can be the key reason.
I wish I knew. I mean, my first bet would be it's because the southern hemisphere is mostly ocean and we don't do oceans very well. But I wouldn't like to, say that would be absolutely certain. But it does seem as though we're less capable of doing the southern hemisphere right on land than we are on the northern hemisphere.
Okay, thank you. And now from Nazareddin, sorry for Adam, and she would like to know how could be integrated the conflict-related fires. How can be integrated in the wildfire modeling? How are such anthropogenic injection, especially in a urban area? Do you just have some insight, or I don't know?
I'm afraid not. One just hopes that we stop having anthropogenic emissions caused by war. But, it's just another one of those problems that we're not going to be able to put into the models.
Yeah. And thanks. So from Olga Vigat, and she is asking about if is the indicator of a duration of wildfire season better captured than other model outputs. If yet, that could be a powerful message for managers, couldn't it? So about the duration of wildfires.
I think this duration of wildfires to me is very interesting from a management point of view, because it does say that, that we need to have capacity for it potentially through the whole year. Whereas at the moment, we tend to sort of have, especially in many areas where it's volunteer firefighting, then the capacity is there during the maximum fire season, but not the rest of the year. So if it's true that the fire season could extend as our probabilistic model suggests, then it's true that we're going to have to invest a lot more in capacity to put them out. So I think that's important. I think the other thing about it is that you also have this situation where the maximum strength of the fire or the number of fires we're also predicting to increase in the future, and that's going to mean many more interventions, which again is an issue of how much capacity we have. And then if you think about it the other way around, at the moment, especially in Europe, but in other places too, there's a whole push for integrated fire management, in other words, doing things to prevent or minimize the risk of big fires, and especially to minimize the risk of fires close to cities and so on. So in Europe, we're doing a lot more prescribed burning, but those prescribed burns take place in intervals when you wouldn't really normally have a fire. So there's special climate conditions. If our fire season increases as much as those predictions suggest, then we're in a situation when you won't even be able to do prescribed burning to minimize the risk of future wildfires. So this is it's an important thing from a management perspective to think about.
Yeah, and it links also to the other point about the strategy of wildfire prediction that every country put in place. And are you able to consider it in the model that you present or in the evaluation, like, or do you see some integration with this information about I don't know if you have this data, these are available, or if you consider in your evaluation?
Well, I think one of the problems here is that we don't have very good information about what management strategies are being used. So we know that there's prescribed burning in Europe. How much prescribed burning there is still very unclear, and when exactly it is. So there's sort of some rules that are out there that say this is when you should burn, but we don't know, when, if they do burn then, and if so, how effective that is. So I think there's a lot of work still to do to test the various techniques that people have put forward in terms of managing fire. Now, if we had that data, it would be relatively easy to plug it into a model, because you basically would say, okay, if prescribed burning happens and it reduces the fuel load by 50%, I can just do that in my model arbitrarily. Yeah. So you could test it, but we need the data basically.
Yep, and I'll just move to the last question because the time is running out, and it's from Alexander Dunant, and he's working on local and regional wildfires in mountain environment. Have you got any take on what specific could target this environment, especially? For the wildfire in mountain environment. Do you have any insight or?
I think one of the key things in terms of mountain, I mean, I'm working globally. So when you start working globally, a number of factors that are important in mountain areas aren't important. One of the things I think in real life is important is the wind speed and what happens to wind speed in uneven terrain. So this is the thing I would look at. We find at a global scale, course scale we're working, that wind speed has no influence on the amount of fire or the amount of burnt area. But I believe that when you come down to these local topographically rough areas, it's going to be important, and that's what I would focus on.
Thank you very much. There is just one request from to share presentation, and the talk, it will be shared on the CMCC channel, and you will receive information to look to watch again this presentation. And I would thank again Sandy for this lecture, and also all people that attended this meeting and stay with us in this hour. And I remind you that there will be the opportunity of this of a session to follow a session on London Climate Action Week at the end of June. So let's hope to see people attending this session in London. And thank you very much, Sandy. I close the meeting here, and thank you all for attending it.
Thank you, Manuela.
Thank you. Have a good day. Bye.
Bye.